Recording is rolling. It is Friday, March 1st. We're going to finish scoring that FRQ from yesterday. Yesterday, you guys remember you did an FRQ in class, and we started scoring it, but just barely before the bell rang. I also, last couple of days gave you guys momentum review quiz. So a couple of students have already turned that in by Monday. So Monday, how about do Monday on the 4th? You guys remember coming up on Tuesday is the SAT for most of you guys. Right? Maybe a couple of guys aren't taking it, but almost everybody is. You guys are juniors. Make sure the blue book is installed on your laptops. That's how you guys are going to take the SAT. Oh, make sure that you come to school Tuesday morning with your laptops fully charged. And then there's a couple of Excel files that I posted to Classroom. One says where you're testing if you are testing. Right? And another is relocations. So if you're not testing, then your first 4 classes are there's a good chance they're being relocated. There is testing in this very classroom, so my first 4 classes, I'm having them relocate those places right there. Right? Right. So you guys good with all that so far? Right. All right. Also, one more thing before we do the FRQ. I want you guys something that's kind of tangentially related to what we're doing. Right? You guys remember there's like something about like a cannon, fire and marbles, like different. We're looking at property of momentum. We're looking at property of kinetic energy. Thank you. Right, so I want to derive for you guys why is kinetic energy 1/2 mv squared? Kinetic energy 1/2 mv squared. I know you guys learned that sort of as a fact a long time ago. Right? I've never quite done a proper derivation of that. So yeah, I want to walk you through that. Right, so I'm going to start with a work energy theorem. Suppose an object starts at rest. I didn't quite write that, but can you guys imagine something starts at rest? And then we're going to apply some force for some distance, force and resistance. You guys know it's a transfer of energy. Let's suppose that all goes into its motion, kinetic energy. So it's not changing height. Right? Maybe it's like a net force, right? Something, okay? Right? Is that right? Right. And maybe I want to know, hey, what is kinetic energy? Say as a function of like speed, right? Well, see, I know force times distance is going to be, oh, guys, what's a good substitution formula for force from Newton's second law of motion? Force equals what? Mass times acceleration. Bam. So that's my next substitution right here. Bam, mass times acceleration, right? And then for that acceleration, maybe I could go back and substitute in something like, how is this related to the velocity that it ends up going, right? Which is going to be part of this form of kinetic energy. Right? So what was that, right? This is actually what made me think of this yesterday. I did that more complicated derivation that we're looking at, right? So I got in this this cloud right here is some kinematic work. Here's that third kinematic formula, the time-independent one. Suppose, again, that starts from rest, so just let V naught go to 0, and then you can rearrange this to get what is the acceleration in terms of the distance that it was pushed, right? And so you can substitute that right there. And oh, look, it also has the, the final velocity, so the velocity that it builds up to at the end of that interval, right? So you make that substitution, that looks like that, right? So in brackets right here, I got this expression right here for the acceleration, right? This pushing distance cancels, and you end up with 1/2 mv squared. So yeah, there's kinetic energy as a function of mass and velocity. Right? So let's switch over to that FRQ. Finish scoring that.